In this video, we're going to start taking a look at some optimization that involves distances. And so let's say for some reason we want to find the point on the line y equals 3x plus 2 that's closest to the origin. Right? So let's just get an idea of what we're looking at. So y equals 3x plus 2 has an intercept of 0, 2 and a slope of 3. All right, so basically what that's saying is that for every change in x1, that's going to go up 3. And so if this is a point on the line right here, 0, 2, then we would move to the right one and then up 3, or the left one and down 3. So another point would be -1, -1. And this is what our line is going to look like. All right, so just geometrically, I know that's not a good line. And we're trying to find the point on that line that's going to be closest to the origin. All right, and we would probably expect it to probably be somewhere in here. All right, so it might be this point right here, somewhere along the line. So it might not be a bad idea just to draw it so you can get an idea of what the distance, and I'm going to call that distance d, just so we get an idea of what we're looking at here. Now, let me erase just a little bit of this. No, that was a lot of it. I'll just redraw it, no big deal. However, what we need to do is we need to do this analytically. All right, so there's our drawing again. Not much better, but a little bit better. And so just like we did before, we're going to set up what the preliminary and secondary equations are. All right, now, what are we trying to optimize? Well, we're trying to optimize the distance. And you might remember from pre-calculus, a formula for distance would be x2 minus x1 square plus y2 minus y1 square. And in this case, well, we have the origin, which is the point 0, 0, so that could serve as one of the points. And then on this line, we would have x, and then y is equal to 3x plus 2. And that's all the points on this line. All right? So let's just substitute. Let's say that this is going to be x1, y1, and then the origin would be x2, y2. And we're just going to substitute back into the preliminary equation. And of course, there begs the question, what is the secondary equation? And the secondary equation is actually given to us very easily as y is equal to 3x plus 2. That's the equation of the line. So now let's substitute. Right, so going back to our steps, so we're going to have our distance d is equal to the square root of, we said that this could be, well, let's flip it around. Let's make this x2, y2. It doesn't really matter. I'm just doing this for simplicity's sake, so we can stay away from negatives if at all possible. All right, so let's just go ahead and say x2 is x, and x1 is 0, and y2 is 3x plus 2, and 0 is going to be y1. Okay, or if we wanted to simplify this, the distance d is going to be equal to the square root of x squared plus 3x plus 2 quantity square. If we wanted to, we could FOIL out that 3x plus 2. So we could write that as x squared. And remember, this is 3x plus 2 times 3x plus 2, not 9x squared plus 4. All right, so you have to FOIL it out. So that would be 9x squared plus 6x plus 6x plus 4. Finally, we can write d very nicely as 10x squared plus 12x plus 4. All right. The feasible domain is anywhere on the curve, okay, or in this case, anywhere on the line. All right, so step 3, the feasible region or the feasible domain, x is in the real numbers. All right, and it's feasible that it could be one of the points like way out here. All right, but in our mind, it's probably somewhere within that orange circle that I created. All right, it's probably a pretty good estimate. All right, but again, that's just what we think. All right, now Step 4 is to take the derivative, all right? And before we do that, with distance problems only, all right, so let's make this apparently clear. With distance problems only, if we optimize the square of the distance, we optimize the distance, okay? So, and that's true only for distance problems, all right? So at least in these types, okay? So there's probably other problems out there that this would work for, but in our scenarios, you can't just square the, you just can't square the preliminary equation every time and expect it to work out, all right? In this case, it does. And think about this, if the distance is the closest point, then the square of that distance would be smaller than any other square of any other distance. All right, so just try to rationalize that for yourself, or you can just accept it. All right, but since d is equal to the square root of 10x squared plus 12x plus 4, which we got just a moment ago right here, d squared is going to be equal to 10x squared plus 12x plus 4. Now imagine taking the derivative of this first expression, and you would have to use a chain rule to be able to do that, and you would get a negative exponent, and it would just be really ugly to do that. All right, this is much easier to work with. So that's why I'm recommending that you just find the square of the distance. I'm going to call this d squared, or d squared divided by dx. So I'm just finding the derivative basically. That's going to be 20x plus 12. We're going to set that to 0. And now you can see very easily that we subtract 12 from both sides. So 20x is equal to negative 12. And then we divide by 20. So 12 20ths, they're both divisible by 4. So that's going to be negative 3/5 is our value for x. Recall that y, all the way back up, is 3x plus 2, right? Remember, y is equal to 3x plus 2. So we just go down here. Y is equal to 3x plus 2, which is the same thing as 3 times negative 3/5 plus 2. That's going to be negative 9/5 plus 10/5. If I was to get a common denominator for 2, 2 over 1 is the same as 10 over 5. And that's going to be 1/5. And so the point that we're interested in is going to be the point x is negative 3/5 and y is 1/5. Now, does this make any sense whatsoever? All right, so let's go back up. And remember, our point that we're hoping is going to be negative 3/5, 1/5. That looks pretty good, right? Because we would go, remember, this is 1 or negative 1, and this is positive 1. All right, so the point is pretty close to what we guessed in the initial part of this. So that's what you want to do, is you want to make sure that whatever you get for your answer, it makes sense. All right, we certainly don't want it to be down here, because this distance would be much longer. All right, so this looks like a pretty short distance and a pretty good answer. By the way, these are 5s in English. What is the minimum distance, by the way? And that should be a problem that we think about. Remember, distance is 10x squared plus 12x plus 4. So the distance is equal to the square root of 10x squared plus 12x plus 4, which is the same thing as the square root of 10 times negative 3/5 squared plus 12 times negative 3/5 plus 4. And what we're going to do is we're just going to stick this in the calculator. All right, so bear with me real quick. By the way, this is the same thing as negative 0.6. All right, that way I don't have to sit there and try to type in 3/5 the whole time, or negative 3/5. So we're going to say square root of 10 times negative 0.6 squared plus 12 times negative 0.6 plus 4. All right, it's probably not going to be an exact answer, but regardless, 0.6325, all right, units, whatever those units might be, meters, centimeters, kilometers, miles, blah, 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 doesn't really matter. All right, so that's going to be approximately 0.6325, I think it was. Yep. Units. Okay, I'll just say UN for units, so that way we understand that there probably should be some sort of measure that goes on with this. All right, so I think in my math lab, there might be a problem where it asks you to approximate 2 decimal places what the distance might be. So just illustrating how you guys might do that. Okay. All right. So what I would suggest is go through, see if you can work this last problem, all right, on your own. So find the point P on the line. Y is equal to 6x. That's closest to the point 740. All right. And then what is the least distance? All right. So you could basically just utilize this video that we just created and try to work that problem and then go through and see if your answer matches the work that I did.